Hello, this is Yashveen. In this video, I'll be solving paper 2 variant 3, October-November 2017, 9701 chemistry. So starting with question number 1, combustion data can be used to calculate the empirical formula, molecular formula, and relative molecular mass of many organic compounds. Combustion data cannot distinguish between different structural isomers. A. Describe the term structural isomers. So any isomer So isomers that have the same molecular formula, that is the same number of total atoms in the compound, and different structural formula based on branches, position, or functional group. So you just write down the definition. B is a hydrocarbon, and the number of carbon and hydrogen atoms in this compound is unknown. A gaseous sample of P occupied a volume of 25 cm³ at 37 degrees Celsius and 100 kilopascals. The sample was burned completely in 200 cm³ of oxygen, which was excess. The final volume measured under the same conditions as the gaseous sample, so that the water produced is liquid and its volume can be ignored, was 150 cm³. Treating the remaining gaseous mixture with concentrated alkali to absorb carbon dioxide decreased the volume to 50 cm³. So all of the volume of carbon dioxide has been removed from 150 cm³, and that decreased the volume to 50 cm³. And since only carbon dioxide has been removed, when you subtract 50 from 150 is only carbon dioxide, the volume of carbon dioxide that is produced. Now 50 cm³ here is the volume of oxygen remained due to it being excess in the beginning. So you can subtract 50 from 200, which would give you the volume of oxygen which was used in the reaction. Use the data given to calculate the value of X. So X is the simplest ratio over here. So we know that we had 25 cm³ of P, and we can subtract 50 from 200 to calculate the volume of oxygen which is used up, and that was 150. And the volume of carbon dioxide which was absorbed after being produced is 150 minus 50, which is 100 centimeters cubed. Now we're supposed to simplify the three values into their simplest form, and dividing all of them by 5, you'll have 5 5s are 20, 25, 5 30s are 115, and 5 20s are 100. And you would then further simplify this to get the numbers 1, 6, and 4. So 4 corresponds to the number of to the value of X, therefore it is 4. Use the data given to calculate the value of X plus Y over 4, which is nothing other than the value of the number of moles of oxygen that reacts according to the equation. And as we calculated this value over here, it is 6. If you were unable to calculate values in B1 and 2, use the data in this box for remaining parts of this question, which are not correct values. But since we have already calculated the values, we don't need this piece of information. And we're supposed to calculate the molecular formula and empirical formula of P. Alright. Its value of X is 4, and the sum of X plus Y over 4 is 6. So we know that there is a total of 4 carbon atoms. So X has to be 4. We can now calculate the value of Y. So we know that X plus Y over 4 is equal to 6. And so to calculate Y, we multiply both sides with 4, which gives 4x plus y is equal to 24. To calculate y, you have 24 minus 16, and therefore y is equal to 8. So the formula of P is C4H8, the molecular formula. and the empirical formula is its simplified version. So you divide both values with 4, which gives the value as CH2. P is unbranched. Give the skeletal formula of two possible structures of P that are positional isomers of each other. So first thing you notice is that the number of hydrogen atoms is twice the number of carbon atoms, which means P has to be an alkene with a single double bond. So here you can change the position of double bond to draw the skeletal formula. So we have 1, 2, 3, and 4 carbon atoms. Similarly, we have 4 carbon atoms over here too. And so in the first isomer, I'll draw the double bond between the first and the second carbon atoms. So in the second isomer, I'll draw it between the second and the third carbon atoms. Use the general equation to calculate the mass of P present in original 225 cm cube gaseous sample, which was measured at 37 degrees Celsius and 100 kilopascals. Give your answer to 3 significant figures. So we have the gas equation. PV is equal to nRT, and N stands for number of moles, which is nothing but mass over molecular mass times RT, and we're supposed to calculate this mass. So making it the subjective formula, we have PV times molecular mass over RT. So for this, we need the molecular mass of P, which is 4 times 12 plus 8. This gives the value as 56. We also need the volume in meters cubed. So you divide 25 with 10 to the power of 6. And therefore the mass is pressure, which is 100 kilopascals times the volume, 25 over 10 to the power of 6, multiplied by molecular mass, which is 56, and then you divide all of that with the value of R, which is 8.31 times temperature. Now you need to convert degrees Celsius to Kelvin, so you add 273, and this gives the answer as 0.0543. Question 2. The halogens chlorine, bromine, and iodine and their compounds show a variety of similarities and trends in their physical and chemical properties. A1. Give the colors and states of chlorine, bromine, and iodine at room temperature and pressure. So chlorine is a green gas, bromine is a brown liquid, orange brown. You can write either of those colors. And lastly, iodine is a gray solid. Part 2. Halogens become less volatile down the group. Explain this trend in volatility. That is, the temperature required for the liquid to evaporate increases. So this temperature is required to overcome the intermolecular forces between the molecules of halogens, and which in this case are van der Waals forces due to induced dipoles. And the number of electrons is what plays the greatest role in these intermolecular forces, which increase down the group. So as you go down the group, the strength of intermolecular forces or van der Waals forces increases. Therefore, the temperature required to convert liquid to their vapor form increases. B. The halogens are oxidizing agents. State and explain the trend in oxidizing power of the halogens. For a halogen to act as an oxidizing agent, it would have to be reduced itself, or in other words, it would have to gain electrons. And the strength required to gain electrons depends upon the nuclear attraction, which acts on electrons that are supposed to be gained, and which in turn is dependent on the shielding. And the greater the number of electrons, the greater the number of shells, and therefore the greater the shielding, which is basically the shielding of outer electrons from the nucleus. If the shielding is greater, that is, the nuclear attraction for valence electrons decreases, and therefore the attraction that is required to gain electrons or to get reduced decreases. And that is why the strength of halogens as oxidizing agent decreases down the group, because the number of electrons increases, the shielding effect of valence electrons increases, the nuclear attraction for valence electrons decreases, and therefore it becomes harder and harder to gain electrons or get reduced, in other words. C. Concentrated sulfuric acid reacts with sodium halides. 1. State any observations that would be made on addition of concentrated sulfuric acid to sodium chloride and sodium iodide. So with sodium chloride, it only acts as an acid, forming hydrogen chloride and the salt sodium sulfate. Whereas with sodium iodide, it acts as an oxidizing agent, forming a mixture of products. And since hydrogen chloride forms in the first reaction, that would be observed as white fumes. And in the second reaction, we have iodine, hydrogen sulfide, sulfur dioxide, and all of those gases. So the appearance you'd observe is of iodine, which appears as purple vapor. To give reasons for the difference in the observations in part 1. So the reaction over here is dependent on the strength as oxidizing agent. Sulfuric acid acts as an acid in the first case because it is not strong enough of an oxidizing agent to oxidize the chloride ion. So in the first case, chloride ion is more strong of an oxidizing agent than sulfuric acid, whereas compared to the iodide ion, iodide ion is a weaker oxidizing agent, therefore it gets oxidized by sulfuric acid. 3. The addition of concentrated sulfuric acid to solid sodium bromide produces brown fumes and an acidic gas that decolorizes acidified potassium manganate solution. Acidic gas in this case is sulfur dioxide. This acidic gas is a significant contributor to acid rain. Write the equation for the reaction of concentrated sulfuric acid with sodium bromide. So the first step in the reaction is the reaction between sulfuric acid and sodium bromide to form sodium hydrogen sulfate and hydrogen bromide, which then reacts in step 2 with sulfuric acid to form bromine, water, and sulfur dioxide. And since the question here has mentioned the acidic gas or sulfur dioxide, you have to write an equation or two which mention sulfur dioxide. So I'll break the equation down into 2 steps. The aqueous solution Z contains a mixture of sodium chloride and sodium iodide. 1 excess silver nitrate is added to Z in a test tube. A yellow precipitate forms. Explain the color of this precipitate. So the yellow colors form due to the precipitation reaction that forms the precipitate silver iodide. Aqueous ammonia is then added to test tube in 1. The mass of precipitate decreases. We're supposed to explain this observation. So addition of aqueous ammonia dissolves the precipitate, which was silver chloride, but the precipitate silver iodide remains as it was insoluble. So silver chloride dissolves in ammonia and silver iodide remains insoluble. 3. Sulfur trioxide is manufactured from sulfur dioxide and oxygen by the contact process, and we're given the equation for the reaction. A. The enthalpy change of formation of sulfur dioxide is negative 296.8 kilojoules per mole. 1. Define the term enthalpy change of formation. So here you write down the definition, which is to use the data to calculate the enthalpy change of formation of sulfur trioxide. Alright, so I'd like to write down the equation again over here. Let me just replace this double-headed arrow with a single-headed arrow for the sake of solving this over here. Right, so the enthalpy change of this reaction is negative 196. Right, and we're also given that this enthalpy change of formation of sulfur dioxide is negative 296.8. So this question requires the formation of a Hess cycle to solve and get to the answer. I'll draw three boxes. One of them is going to be a box for reactants, another one for the products, and then here we're going to have the elements, which is of course sulfur and oxygen. You don't need to balance this, however you can if you wish to, but since it's not required and I'm only going to explain the steps, so I'll just write it unbalanced. So you need to draw the arrows from the elements to their compounds. Since this is a formation, the start of the process is going to be the box which contains elements. So I'll write start over here, and the end is going to be the products. That means this arrow over here is going to be equal to these steps, which include going from elements to sulfur dioxide and then going from sulfur dioxide to sulfur trioxide. Let me explain that. So here we need to calculate this value, which is formation of sulfur trioxide, but let's denote it by x, but I'll write twice of x because over here we have 2 moles of sulfur trioxide forming according to the equation, and formation enthalpy change of formation is supposed to be enthalpy change for formation of 1 mole only. So I'll be writing 2 moles over here. Similarly, we are given with formation of sulfur dioxide, which is negative 296.8. I'll multiply that with 2 since we have 2 moles of sulfur dioxide forming over here. Now we have drawn the Hess cycle and we're supposed to form equation and then find the value of x. So 2x is equal to twice of negative 296.8, and then you add the second value, which is negative 196, and solving this you get the value of x as negative 394.8 kilojoule per mole. You can use this method whenever you are given with enthalpy change of formations data and you're required to calculate any of the three values, be it between the one which is the actual value of enthalpy change of reaction or the formation of any of the reactants and the products. B. The contact process is usually carried out at a temperature of approximately 700 Kelvin, a pressure of approximately 150 kilopascals, and in the presence of a vanadium oxide catalyst. The Boltzmann distribution of a mixture of sulfur dioxide and oxygen at 700 Kelvin is shown. EA catalyzed represents the activation energy for the reaction in the presence of the catalyst. So here's the diagram. Add a labeled EA uncatalyzed to the diagram to indicate the activation energy in the absence of the catalyst. Alright, so uncatalyzed reaction would mean the reaction would have a higher activation energy, and that would mean it would be ahead of the EA catalyzed reaction. So I'll mark that somewhere over here because the value of energy is supposed to be greater. It would move ahead of the activation energy of catalyzed reaction. To state the benefit of using a catalyst in this reaction and explain how this effect is achieved. So using a catalyst of course increases the rate of reaction by providing an alternate route with a lower activation energy. And since the activation energy is lowered, that means there are more molecules that have sufficient energy to react. 3. State and explain how an increase in pressure would affect both the rate of reaction and the yield of sulfur trioxide in the contact process. So increasing the pressure would increase the rate of any reaction because the molecules would be closer together, as there are greater number of reactant particles per unit volume, which means there would be far more collisions in per unit time. So you can start by writing that. And the yield in this case would also increase because whenever you are asked about yield, it has to do with the equilibrium. And according to Le Chatelier's principle, whenever a change is introduced to the equilibrium changes to oppose this change. And in this case, let me go back to the equation. So increase in pressure always favors the side that has fewer molecules. As you can see over here, there's only 2 molecules of the product and 3 molecules of the reactants. So clearly the side with fewer molecules is the right hand side, or the side of the product. So if you increase the pressure, the equilibrium would shift to the right hand side to favor formation of products. And therefore it would decrease the pressure as there would be fewer molecules in the reactant after equilibrium has shifted. Therefore, it would also decrease or oppose the change which has been caused by increasing the pressure. See, at a pressure of 1.5 into 10 to the power of 5 pascals, 1 mole of sulfur dioxide gas was mixed with 1 mole of oxygen. The final mixture formed was found to contain 0.505 mole of oxygen. 1. Calculate the amount in mole of sulfur dioxide and sulfur trioxide in equilibrium mixture. So let me draw the ice table, or first I'll write the equation. So in questions requiring the pressure constant or the concentration constant, you can use the following method by writing down the equation, and then you use the letters ICE, I which stands for initial amount, C is the amount which has changed, and equilibrium is the amount which is present at equilibrium. Now you'd understand this when we're solving this. So 1 mole of sulfur dioxide reacted with 1 mole of oxygen, and since there is no molar amount of sulfur dioxide mentioned, we'd assume it is 0 initially. And the final equilibrium mixture, that is at this point, at the last stage or at equilibrium, contained 0.505 mole of oxygen. So you have 0.505. which when you subtract from 1, you get the value as 0.595. So 0.595 is the value of oxygen and the mole of oxygen that has reacted, and you write that over here. 0.495 is the value that has been used up, and therefore you put a negative sign over here. Similarly, you would also subtract from the value of sulfur dioxide. Now you're going to multiply 0.495 with 2 to get the value of sulfur dioxide that has been used up, because for every 1 mole of oxygen, 2 moles of sulfur dioxide react. So that is how you get the volume of sulfur dioxide that has been used up. You're supposed to put the opposite sign, which in this case will be positive, and over here this is going to be 0.99, just as it was with the reactant sulfur dioxide. So 1 minus 0.99 is 0.01, and this over here is going to be 0.99. So the molar amount of sulfur dioxide is 0.01 and sulfur trioxide is 0.99. Calculate the partial pressure of oxygen in the mixture, equilibrium mixture. You divide the number of moles of oxygen at equilibrium with the total number of moles and multiply this with the total pressure. Okay, so to calculate the total number of moles at equilibrium, I'd add up 0.01 plus 0.505 plus 0.99. So this gives the value of total number of moles as 1.505. And for oxygen, we can use the value 0.505 divided by 1.505 times the total pressure, which is given in the question as 1.5 times 10 to the power of 5, and this gives the partial pressure of oxygen as 5.03 times 10 to the power of 4. In another equilibrium mixture formed from different starting amounts of sulfur dioxide and oxygen, the partial pressures of sulfur dioxide, oxygen, and sulfur trioxide are shown. Right, the expression for equilibrium constant for the production of sulfur trioxide from sulfur dioxide and oxygen. All right, so you write down. So you have the products in the numerator, which is sulfur trioxide, the partial pressure of sulfur trioxide, and you square it because in the equation we have 2 moles of sulfur dioxide, and then you divide it by the reactants, the partial pressure of reactants. Similarly, sulfur trioxide's pressure would also be squared, and then you multiply that with the partial pressure of oxygen. Calculate the value of Kp for this reaction and state its units. Alright, so using the formula we have so this is going to be our calculation. Square that times the partial pressure of oxygen, which is 6 times 10 to the power of 4. Right. Now this gives the value as 0.195. I have rounded it off to 3 significant figures. Now coming to units, we have 2 units in the numerator and denominator contains 3 of those. So 2 of these are cancelled from the numerator and denominator, which leaves us with 1 over Pascal. So that is equal to Pascal to the power of minus 1. 4. A, B, and C all have the formula C4H8. They all decolorize bromine and are structural isomers of each other. So they have a single double bond. A. State the name of the process by which A, B, and C could be obtained from C10H22. So obtaining a smaller chain hydrocarbon from a larger one can be done by the cracking process. B. Draw the structures of the 3 structural isomers. So in the first 2, obviously, what you can do is place the double bond between the first and second carbon atom, and in the other one you can place it between the second and third carbon atom. In the third one, you can have this alkyl group bonded to this carbon over here, and the first carbon bonded to 2 hydrogen atoms only. So you can write that as C. Only A shows geometric isomerism, that is cis-trans isomers. So this is going to be A, since this is the only compound which has carbon in the double bond bonded to 2 different groups of atoms. 1. Explain the meaning of the term geometrical isomerism. So these are geometrical isomers, first because they are stereoisomers, because they have the same structural formula but differently out of atoms, and in stereoisomers they have to be either geometric or optical, and they are geometric because there is a double bond between carbon atoms which prevents rotation. 2. Draw the displayed formula of A and use it to show the mechanism of reaction of A with hydrogen bromide. Include all necessary charges, dipoles, lone pairs, and curly arrows. So the reaction of A with hydrogen bromide is an electrophilic addition. It's addition because the double bond is involved and hydrogen bromide acts as an electrophile over here. So you can start by drawing the displayed formula of A. Alright, so the proximity of hydrogen bromide to the pi bond induces a temporary dipole on hydrogen bromide because the electron dense region in the pi bond between these two carbon atoms repels the electrons away from hydrogen towards bromine. You might wonder why it's hydrogen that has its electron repelled away and not bromine, because bromine is more electronegative, so it tends to attract, it's more electronegative than hydrogen, so it is going to attract electrons, and as a result it will gain a partial negative charge, and hydrogen will have a partial positive charge. Now the one of these bonds is sigma bond and the other bond is pi bond, so there is an electron from one of the carbon atoms in each of the two bonds. Say the cross represents the electron from this carbon atom, and this dot over here represents the electron of the second carbon atom so these two electrons are involved in the sigma bond. Now in the pi bond, similarly, there are two electrons, so these two electrons are going to be pulled away, so they are going to be shared between this carbon atom and hydrogen, and therefore the carbon atom over here loses an electron, and that is the reason it gains a positive charge. So the first step over here is that you don't need to draw these electrons, so I'll erase them. I'll only draw them for explanation purpose. We have carbon bonded to methyl group and hydrogen, and the electrons from the pi bond are lost to this bond between carbon and hydrogen, and that is the reason the second carbon atom, which was initially involved in double bond, has now has a charge of +1. And over here, now that hydrogen gains electron from this bond, it doesn't need the bond from this covalent bond with bromine anymore, so it loses the electron from this bond over here, which are lost to bromine, and due to having an extra electron, bromine now has a charge of -1, and this is attracted to the positive carbon, so it reacts with the carbon over here in the carbocation. B does not show geometrical isomerism. B reacts with hydrogen bromide to form a mixture of two structural isomers, X and Y, and X has a chiral center, which is produced in a higher yield than Y, and Y does not have a chiral center. One, state the meaning of the term chiral center. So it is the carbon atom which is bonded to four different groups, which is single bonded to four different groups of atoms. Name B. Alright, so let's decide which structure is B. So we're given in the question that one of the products of B is supposed to have a chiral center. If you look at this structure over here, let me draw the possible products. It can be either bromine on the first carbon chain and the hydrogen on the second carbon chain, the second carbon which is bonded to two methyl groups. Now this is not a chiral compound, since this carbon atom is bonded to two same groups. This is methyl group over here, and neither is this carbon because it is bonded to two hydrogen atoms. Let's look at the other possible product, which could have been hydrogen bonded to the first one and bromine bonded to the second carbon atom. This is not a chiral product either, so this is not B. This was A, this is B. let me just draw B over here, which is CH2CH, CH2CH3. Right. Name B. You have a straight carbon chain with double bond in the first position, so this is but1ene. X exists as a pair of optical isomers. Draw these isomers using the conventional three-dimensional representation. So X is the product of reaction of P with hydrogen bromide that forms a chiral product, right? So this can give two products when one of those products can have hydrogen bonded to the first carbon atom, which was involved in the double bond, and bromine bonded to the second atom. I'm not going to write down all of the hydrogen atoms. I'm just going to represent by these small arrows, and I'll draw the second product over here. Right, so the second product would have bromine bonded to the first carbon atom and hydrogen bonded to the second carbon atom, and the rest of the structure. So now this product over here is not a chiral product because it does not have any carbon atom that is single bonded to 4 different groups of atoms. However, this can be because this carbon atom over here is bonded to hydrogen, bromine, a methyl group, and an ethyl group. So this is an optical isomer, and I'll draw that over here. So you're supposed to draw this in the tetrahedral layout of the carbon, which is bonded to 4 different groups of atoms. So you have the bold wedge going out of the page. This can have CH2, CH3, and then the one which is going into the page, and then the last one. So the way you draw it over the mirror plane is you draw the carbon as it was, the hydrogen as it was, and the other group. The only thing that differs is you draw these two which are closest to the plane, mirror plane, and you draw them as if it was reflected over this plane. That is, I draw the wedge again, bonded to CH2, CH3, and then the dotted wedge bonded to bromine. So you see, this has to be a reflective superimposable image. These two have to be superimposable images of each other. Explain why X is produced in a higher yield than Y. Let me draw the two possible mechanisms. So we had the double bond over here, CH2, CH3. So X, which has bromine bonded to the second carbon, comes in a higher yield than Y, which has bromine bonded to the first carbon atom. Right. So bromine bonding, the bond which forms between carbon and bromine, is the last step because it is a step which includes the bond formation between the carbocation and bromine. Now let me erase this bromine over here so I can better explain. So initially, after hydrogen had bonded and the double bond was broken, we would have a carbocation. In case A, which produces X, the carbocation, these are hydrogen atoms over here by the way. Case A, which forms X, is formed from a secondary carbocation because this carbon atom has two alkyl groups bonded to it, one over here and the other over here, as opposed to case B, where the carbon atom with the positive charge in the carbocation has only one alkyl group bonded. So the greater the number of alkyl groups bonded to the carbon with the positive charge, the more stable the carbocation is, and the carbocation with greater stability forms the product which has higher yield. And that is so because when surrounded by carbon atoms, the positive charge on the carbon atom decreases as these carbon atoms tend to pull away the electrons from this positive carbon. And over here, however, only one carbon is close to the positive carbon. The rest of the two are far away. They do have a positive inductive effect of pulling electrons and therefore decreasing the positive charge of carbon, but they are so far away that the effect is reduced. Therefore, the carbon, which has greater number of alkyl groups bonded to it, is more stable, has a lower activation energy to form product, and therefore it forms product in greater yield. E. C does not show geometrical isomerism. C reacts with hydrogen bromide to form a mixture of two structural isomers, neither of which has a chiral center. Name C. Alright, let me go back to the question. This one was A, this one was B, and that means this has to be C. I'll draw that with the question so we don't have to scroll back up. Alright, so I'll draw this split formula over here. So we have carbon bonded to hydrogen and double bonded to another carbon atom, which is single bonded to two alkyl groups. To name it, we first have to recognize the straight chain. In this case, this can be either this one over here, or it can be this chain over here. Doesn't really matter because it would give the same name anyway. So the main chain has 3 carbon atoms. That means it has to be propene, and since the methyl group is on the second carbon atom, the branch would be named as 2-methyl, and as you can see, the double bond is between the first and the second one, so it would be 2-methyl prop-1-ene. You always start by naming the branch first. To draw the displayed formula of each of the structural isomers produced by the reaction of C with HBr, with hydrogen bromide. Alright. So in the first case, we can have the carbon atom bonded to hydrogen and the second one bonded to bromine. And the rest of the structure follows out. You have to draw a tetrahedral structure. I don't have much of space, so I might be going out of the boxes, but remember you have to stay within the space provided to you. So we have the backbone over here with the methyl group on the second carbon atom, and in this case the bromine can be bonded to the first carbon atom, making it a structural isomer, and the rest of the hydrogen atoms bonded to carbon. This is it. We're done with this paper. Thank you for watching.